All right, so Thursday morning, again, last day this week. No class next week. We'll pick back up Monday after the 4th of July. Uh, I might strongly encourage you, the next week you have off to spend a little bit of that time off uh, working on mechanics and materials, working on those homework problems. So when you we come back on July 6th, then you have questions about anything, we can hopefully resolve those. Monday we get back, and the following day on Tuesday we'll take our test. So again, the test just goes up through chapter 5. The last thing we did was twisting statically indeterminate members with a circular cross section. Very briefly, the end of class yesterday, we started talking a little bit about shear and moment diagrams, and that's what we're going to talk about today. Remember, though, this will not be on your test, test number 2, when you get back on after 4th of July. What we're going to talk about in chapter 6 will be on test 3. All right, so any questions about anything before we get started? All right, well, I guess was in your textbook. This is in chapter 6, the first section in chapter 6. We're talking about shear and moment diagrams. So as I said yesterday, this is basically just a graph showing what the shear force, the internal shear force, and the internal bending moment is for the entire length of the beam. So if we got some beam, also remember at this point we're assuming we don't have any axial loads on this beam. We'll just have maybe a concentrated moment applied, or we can have transverse forces perpendicular to the beam, but nothing pulling or the beam in tension or pushing it in compression. And basically we talked about how we had done this before, right? If you came out here to a particular location and cut that beam, you would see these internal shear force and bending moment acting on that cross section. If you look at the right side of where you cut it, you would see the same shear force and bending moment. Magnitude the same, opposite direction. Also, keep in mind the way I've drawn this is what we define the positive directions to be. And we did this in chapter 1, but we did it again at some particular specific location. Right? What we want is, if we put a coordinate system on here, what we want is we want to find equations for V and M as functions of X. X being, again, the longitudinal direction down the beam. So if we can get an equation for the shear force V as a function of X, we can graph that, and that shows what the shear force is down the length of the beam. If we can get an equation for this moment as a function of X, we graph that. That depicts the moment as a function of X down the length of the beam. And this is the first way we're going to look at constructing these shear moment diagrams. There's more than one way to accomplish this. And this is the way we're going to start with looking at first. Now, when we come back after 4th of July, I'm going to show you a different method that we can use to construct the shear moment diagrams that's maybe a little bit quicker, easier, a little bit shorter, less work involved. But it's important that you learn how to do it this way, because this is a skill you're going to have to use a little bit later when we get to beam deflections. So this is something you're going to have to know how to do anyway. So it's a good thing to learn how to do it now. So that's basically where we're at. One other note maybe, and then we'll just start right in and work one of these. Again, there's nothing new involved as far as there's no new formulas or nothing new involved. So, but one thing I will just a note to keep in mind: these equations for the shear force V and bending moment M are going to change wherever the loading changes. So the equations for V and M will change where the loading changes. So everywhere we have a change in the applied load to this beam, these equations are going to change. This is going to determine how many times we're going to have to cut this, and we're going to get a separate set of equations for V and M on each of those sections of the beam, again, determined by how many times the loading changes. All right. All right, so again, pause for just a second. Any questions before we see if we can solve one of these problems? All right, I'm assuming everybody's got everything you want off this first sheet. I'm gonna go ahead and go to a new page, so maybe we'll have enough room to do this all on one sheet. All right, so let's see if we can draw the shear and moment diagrams for this beam. All right, so we've got a beam. Let me draw the picture. We've got a pin support here. This is B. We've got a roller out here at this end. This is, we'll call this point D. And this end we'll call A. And we've got a 30 kilonewton force acting straight down at the left end of that beam. Here at C, this point C, we've got a 50 kilonewton force acting straight down at C. And we need some dimensions. Between A and B is looks like 1 meter. Between B and C is 3 meters. And between C and D is 2 meters. So let's see, I think I got all my dimensions. And 2 forces applied. All right, so this is our beam. It's an overhanging beam. We got that left ends hanging out over our pin supported beam. All right, well, the first thing we need to do before we're going to start trying to construct or draw our shear moment diagrams, we need, in order to find our equations, we need to know what the support reactions are. Now, at this pin support, we're going to have a vertical support reaction we'll call By. We'll have a horizontal support reaction, or at least it's capable of providing a horizontal support reaction. And here at our roller, we just have a vertical support reaction. Now, we don't have any other forces in the x direction. That was the assumption I mentioned a minute ago. We're assuming at this point there are no axial loads. The only two applied loads are vertical. And so just by observation, Bx is going to be 0. There's no horizontal force necessary or needed at that support reaction. So we need to find By and Dy. And we apply our equilibrium equations to the whole structure. So we're looking at the entire beam here. We haven't cut it yet. We're going to do that in a minute. And we want to find our support reaction. So we could sum the moments about B and get dy, or we could sum the moments about D and get By. One or the other. We're going to find them both, so it doesn't matter which one you do first. So I'm going to sum the moments about B and set that equal to 0, and I should be able to find what dy is. So if positive is counterclockwise, we have dy times 5. And then we'd have, or I can just work in right to left, 50 times 3 would be a negative moment. And then the 30 kilonewtons causing a counterclockwise moment, so positive 30 times 1 equals 0. And solve, we get dy. I got 24 kilonewtons. Now, once we know what dy is, we could sum the moments about D and get By, but when you have a choice, it's always better to just sum the forces than it is to sum the moments. Sum the moments, if you do it correctly, you're going to get the same thing, but there's more places to make mistakes summing moments than it is forces. So, simplest thing, just sum the forces in the y direction, set that equal to 0. By, I assume, is going up. Dy goes up. And then we got the 30 and the 50 going down. And I think that's it. Those got to add up to 0. I got By was 56 kilonewtons. All right, so just basic simple statics. 2D equilibrium problem. Found our support reaction. All right, so as I mentioned just a minute ago, our goal is to get equations for V and M, right, as a function of x, where x being the, put our coordinate system on here. If I can draw a straight line down this beam. That's not real straight, but it'll do. So if we've got our xy coordinate system with our origin at this end, we want an equation for V and M as a function of x. And as I mentioned, those equations are going to change everywhere the load changes. So we're going to have one set of equations for V and M here between A and B, right? But we got this support reaction there. The load changes. So we're going to get a different set of equations for this section of the beam between B and C. Because at C, we've got this 50 kilonewton force. The load changes, the equations will change, and we'll get a third set of equations for this part of the beam between C and B. So this is going to require us to cut this beam 3 different times. Right? So first thing we're going to do is come here somewhere between A and B. Now we're going to come out here some arbitrary distance x, rather than the problems like you did in chapter 1, where you went to some point, that maybe was half a meter from that end, and you found the internal forces at that particular location. Here we're going to this arbitrary location, some distance x from that left end. And so that's what we're going to do first, is we're going to look at for section AB. And keep in mind, these equations we get are only going to be valid for that part of the beam. So they're only going to be valid for x values between 0 and b's at 1 meter. So do it the same way. We draw our free body diagram. So when we cut this thing, here's point A. We've got our 30 kilonewton apply force. This is some arbitrary distance x. And at that cross section, we want to find what's the internal shear force and bending moment at that arbitrary cross section. So I'm going to call this, let's say, Vx and Mx, a little subscript, just indicating that's the shear force V and moment M at this arbitrary location X. And we apply our equilibrium equation, solve for those two unknowns. Right? So we, one other thing before I do that, just a note here. I highly encourage, if you want your equations to produce the correct graphs, you need to assume that V and M are in positive direction. So this was not just an arbitrary decision on my part. I intentionally did this. I assumed V and M are in the positive direction. So always do that, which our sign convention here, V goes down, M's counterclockwise. So just sum the forces in the y direction, and we can solve for Vx. Sum the forces in the y. If we take positive up, both of these are going down. Minus 30 minus Vx equals 0. So Vx is equal to minus 30 kilonewtons. And that one you could get probably just by looking at it, but if necessary, write the equation down. Right. Now, to get our moment, we need to sum the moments about a point. And you could sum the moments about any point you want to. We could sum the moments about A and solve for Mx. But this is just a suggestion. Good practice to do would be to sum the moments about this point where we cut it. Maybe I'll call that point P. P for point. So that's what I would recommend, is sum the moments about that point where you cut it. And I'll tell you, the motivation and why I suggest you do that is, if you sum the moments about the point where you cut it, then you eliminate your shear force V. It goes through that point and it won't show up in your moment equation. So if you happen to have made a mistake when you calculated V, you won't compound that error and get the wrong moment. That's that's the motivation for doing this. Yeah, we could sum the moments about A, and now that we know what Vx is, we could solve for M. But again, if we mess V up, now our M's going to be wrong. So don't have to do it this way, but I encourage you and suggest you do, and that's why I'm doing it. So if we sum the moments about P, Vx goes through P, does not cause a moment. I've got my internal bending moment, I'll call it Mx. And the 30 times that distance, which is x, will be a positive moment. So 30 times x. And that's it. Equals 0. Solve for Mx. It would be minus 30x. And these would be kilonewton meters. So what we've done is gone out here some arbitrary distance x, some place between A and B, cut it, and solve for the internal shear force and bending moment at that cross section. Any questions at this point? Because going forward, we're going to do exactly the same thing 2 more times. So any questions about the process, the procedure, how we got these 2 equations? All right. I'm hoping silence means everybody's with me. So we're just going to do this again. We're going to come out here somewhere between B and C. All right. So we're going to come out here, again, some arbitrary distance x, and cut that thing somewhere between B and C. Draw our free body diagram, apply our equilibrium equations, solve for V and M. And just repeat, wash, rinse, repeat, whatever. Doing the same thing, but these equations, right, that we got here, again, they were only valid for that part of the beam. Likewise, the equations we're about to find are only going to be valid on section BC. So these are going to be x values between 1 and 3 and 1 is 4. So we draw our free body diagram. If we cut it somewhere here between B and C, we got to draw everything to the left of where we cut it. So we get our 30 kilonewton force there at A. Here at B, we got By, and this is why we needed the support reaction earlier. I know By is 56 kilonewtons. Right? And we're cutting it before we get to C, so the 50 kilonewtons doesn't show up on this. And again, we're looking at this arbitrary distance x from that left end. And we want to find what is Vx, what is Mx. Again, I'm assuming positive directions here. Now, for as dimensions go, between A and B is 1 meter. And if this whole thing is x, right, so from A to where we cut it is x, then this distance from B to where we cut it, which we're going to need, you'll see in a minute, would be x minus 1. Right, everybody with me there? How I got that distance x minus 1. All right, so now we're ready to go again. Sum the forces, sum the moments, solve for V and M. So summing the forces in the y direction. Again, I'm going to take positive up. So we have 30 going down, 56 going up. I assume V is going down. And I think that's it. So solve and Vx. I might do my math right. It looks like 26, positive 26 kilonewtons. And notice so far, the shear force V for AB and here, they're both constant. But the moment up here was not constant. It's not going to be constant in this section either. Again, I would sum the moments where I cut it. So if we sum the moments about P, take counterclockwise positive. Let's see. So we got our moment mx. All right, we eliminate v. 56 is going to cause a clockwise moment about p, so that'd be a negative moment. 56 times x minus 1. Right? That's why we need that distance. And then the 30 kilonewtons is causing a counterclockwise moment, so that'd be a positive moment of 30 times that total distance, which is x. And that it's got to be equal to 0. And to save time and get through this quicker, I'm going to skip going through all the algebra. You multiply this out, you get minus 56x plus 56, and then combine like terms. I'm skipping the algebra. I got mx was 26x minus 56. Again, these are kilonewton meters. And as you see, it's not constant. It's a function of x. But it's linear, so graphing this is going to be pretty easy. All right, so we're 2/3 of the way there. We got our equations for the section of the beam between A and B. Now we got our equations for section BC. Any questions before we do the last section? All right, so we're going to come out here somewhere between C and D and cut it again. And again, this would be for x values between 4 and 6. Is that right? Yeah, that's right. I just can't add sometimes. Now, there's a reason I'm going to do it this way, because you might be thinking, well, if I cut it here, it'd be less work if I work with the right side than work with the left side. And I'm going to come back to that in a minute. But so if you're thinking that, just hold that thought. But first, I'm going to do it by just sticking with the left side of where we cut it. So we got to have, if we cut it here between C and D, we need everything to the left of where we cut it. So we got our 30 kilonewton force there at A. We've got our support reaction, 56 kilonewtons at B. Now at C, we've got our 50 kilonewton force. And again, we cut it before we get to that end at D. And this is, again, some distance x from end A. I know between A and B is 1 meter. Between B and C is 3 meters. So the distance from where we cut it to C, if this is x and that's 4, this would be x minus 4. Right, we're also going to need to know what this distance is from where we cut it to B would be x minus 1. Right, so any questions at those two distances? And again, what we're after here is shear force and bending moment at that point where we cut. All right, so any question about a free body diagram? All right, well then let's apply our equilibrium equations. We can Squeeze this in here. Sum the forces into y. We got 30 going down, 56 going up, 50 going down, and Vx going down. All those got to add to 0. Solve for Vx. I got minus 24 kilonewtons. Constant like the others. Now, sum the moments about P here. So, again, we eliminate V by doing that. I've got my moment mx. I got 50 times x minus 4. That's a positive moment. The 56 kilonewtons at B is causing a clockwise moment. So minus 56 times x minus 1. And then the 30 kilonewtons finally is causing a positive moment. 30 times x. So I'm going to double check, make sure we got everything. We got our moment. We've got the 50s, the positive moment, times x minus 4, minus 56 times x minus 1, and then plus 30. So I think that looks right. It's all for M. Let's see what I get. Minus 24x plus 144 is a kilonewton meter. Right, so again, the work here is not hard. It's just it's simple 2D equilibrium. There's nothing new or exotic about what we're doing. And we have found formulas for V and M for section AB. Found formulas for V and M between B and C. And now we got formula for V and M between C and D. So now it's just a matter of graphing this. And this is just simple. You learned how to graph back in algebra somewhere long ago and far away. And the graphing here is easy because again, all we have are constant functions and linear functions. Before we do that, though, I wanted to point out why I did it this way when we cut it between C and D, why I stuck with doing the left side. The motivation for that is because if we cut it between C and D, and I'm mentioning this because I see students do this quite frequently. Even though I point out to them in class, if you do it this way, you got to be careful. They still do it wrong, but I'm going to show you. If you cut it between C and D, so just this is just a what if. All right. Let's see. I might have more room. I'll come over here. So if we cut it between C and D, so here's D. We have obviously dy we need to include on that, which is 24 kilonewtons. And that's it, right? If we cut it between C and D, we don't make it to the 50 kilonewton force. And so we want to find, one, we've got to make sure we turn our shear force V and moment directions around. That's one thing students do wrong if they do it this way. But the more commonplace for us is where students mess us up. Is they say, okay, well, I'll come out here some arbitrary distance x and cut it. And I'll be the first to admit, solving for this is a lot less work than what I did up here. But if you do this, you're going to get the wrong equation. It's not going to be correct. And this is what I see students do quite frequently. Anybody have any thoughts or ideas why, if we did this, why we would not get the same equation as we got up here? B would actually turn out to be correct. Moment, not. No ideas why this, if you do this, you don't get that same moment equation? Well, basically what you've done, if you do it this way, is you're using a different coordinate system. You're basically using a coordinate system where the origin is here, positive x is to the left. That's what your equation is going to be with respect to. Not the same coordinate system that we started out using. That's why that moment equation is not going to give you the same moment equation you got here. And it's not going to be compatible with the moment equations you got with the original coordinate system. So what you got to do, if you want to do it this way, you can't change coordinate systems, right? That doesn't work. So what you would have to do is stick with the same coordinate system. Where our origin is way over here, this is the distance x, right? Just like it was up there where you cut it. This distance is not x, it would be 6 minus x. Right? So if you do this, that would give you the same equation. You're using the same coordinate system, and you're going to get the same equation. Now, once you take all that into account, personally, I just prefer to just stick with doing it the way I did up here. But that's me. If you want to come over here, that when you cut it, if you want to work with the right side, you can do so. But you got to keep in mind what we just discussed there. You can't call that x. That makes sense? Everybody with me? All right, so now all we got to do is graph our equations. So I'm going to need obviously, I'm not going to try to squeeze it in here. I'm going to get a new sheet of paper. And I'll refer back to this one because we're going to get make sure we're using our right equations. Does anybody need a minute, or can I go to a new sheet? All right. So I'm just going to put this one on top of this one because we're going to come back to this. So typically when we draw this shear moment diagram, right, I'm going to label these points on here so we'll know where we're at along the beam. And this is going to be our shear diagram. So we're going to graph the shear force. And it's important, students all the time leave off units. Now, it's up to you. You don't have to write the units by, you'll see in a minute, we start putting numbers on here. It's sufficient enough to just put the units once. Just put the units beside V there, and it's understood that all these numbers we're going to put on here are in kilonewtons. But if you don't do that, I'm taking points off because you don't put units on there. All right, so between A and B, go back to the previous, our shear force was minus 30 kilonewtons. So we're going to start down here at minus 30. Right? And notice it's constant. So it does not change between A and B. Doesn't go up, it doesn't go down, it's constant. Now, what happens between B and C, if I can Leave this up. Where's my shear force between B and C is 26, positive 26. So this goes up from minus 30 to positive 26. And again, that's constant. It does not change. So between B and C, it stays a constant value of 26 kilonewtons. And now we have room here. What was between C and D? It was minus 24, so it goes back down. And it goes down to minus 24, and it's constant between C and D. It doesn't change. So we have just constructed our first shear force diagram. Any questions about that? So this diagram shows us what the shear force is anywhere along that beam. You pick any point you want. I can look at and go to this diagram and I can tell you what the shear force is. All right, so now let's do our moment diagram. Go back up here. All right, just like I did before, I'm going to label these points so we'll keep up with where we're at along the beam. And this is our moment diagram. And again, we need units. These are kilonewton meters. And see what I'm just going to write down here. Between A and B, it was minus 30x. Between B and C, what was it? 26x minus 56. And from C and D, it was minus 24x plus 144. All right, so those are just my three equations that we found previously, but now I got everything here on one page where you can see it. All right, so again, this is linear. The graph's going to be a straight line. Oh, and we'll put some dimensions on here because we're going to need values. This is 1 meter. This was 3 meters. And this was 2 meters. All right, so when x is 0, m is 0. So we start here at 0. Slope is negative, right? We're going down. So we're going down this way. And when x is 1, we're at B. So when x is 1, moment is minus 30. So we're going to start here at 0 and go down to minus 30. It's linear. It's a straight line. All right. Any question how I got this part of the graph? Now, one thing you should always check is this moment equation for BC, right, when x is 1, it's where these two meet. They should give you the same value. So always a good idea, check here. When x is 1, what do I get? 26 times 1 minus 56 is minus 30. Same thing we got here. All right, so I'm starting at the same point. And again, the motivation there is this is how you catch and find if you've made a mistake somewhere. If this doesn't start where this one ends, then something's not right. You need to go back and find your mistake. It's almost impossible to do one of these and not know if it's right or not. Everything should check out if not. Now when x is, when we're at C, x is 4. So this is going to give me 26 times 4 minus 56. I got 48. And again, this is for this one. it's linear. So we're going from minus 30 up here to positive 48. And I'll try to draw a straight line. That's pretty straight. So any question about that part of the moment diagram? All right, so we're almost there. We just got to do this last one. Again, check. When x is 4, we should get the same thing that we got where that one ended. We should get 48. And if you do minus 24 times 4 plus 144, better get 48. Somebody's got a calculator, wants to check that. So that checks. It means we're starting here where this one ended. We're starting here at 48. Now when x is 6, I get minus 24 times 6 plus 144. And that better come out to be 0. If it doesn't come out to be 0, I know we messed up. And we'll talk about that Monday when we come back as to how I knew that was supposed to be 0. It's linear. It's a straight line. Goes from 48 back down to 0. So I have now constructed the shear force and bending moment diagram for this beam that we started out with. Now, I mentioned yesterday the reason we need to know how to do this, if we're actually going to analyze this beam and you wanted to calculate what the maximum shear stress in that beam was, you need to know what the maximum shear force in the beam is. Well, I can get that just by looking at this diagram. I know the magnitude of that maximum shear force is, what, 30 kilonewtons. So that's the shear force we would use to calculate our maximum shear stress. Looking at my moment diagram, right, I can look at this and tell. We're just looking at the largest magnitude here would be, what, 48 kilonewton meters. So if I'm going to calculate the maximum normal stress due to bending, that's what I need. I need to know what those maximums are. You get that from the shear and moment diagram. That's why you construct these things. And what we've done today is one method of how to do that. All right? So again, any questions how we accomplish this shear and moment diagram? It's not hard or complicated. Basically, if you know statics, you can do that. Now, just the last couple of minutes we got here, I'll mention on Monday, we're going to talk about a different method. There's a way that you can do this without having to actually calculate those equations. In fact, for this beam, I could construct this shear moment diagram in probably less than a minute and not have to find any of those equations. That's what I'm going to show you how to do on Monday. But you need to know how to do it this way. As I said, this is something you're going to use later when we do beam deflections. You got to be able to find these moment equations like we did here. In fact, last thing, just an observation. If you look at this beam, look at our shear diagram. Where do we start at here? 30. What's that force? 30. What was By? 56. What did we do at B? It's just a preview ahead of what we're going to talk about Monday. If we go from minus 30 to 26, what is that? 56? 56. Not a coincidence. At C, 50. How far did we go down? We went from positive 26 to minus 24. 50. It's going to work that way every time. So basically, if you know the forces, you can draw the shear diagram without having to calculate anything. Now, I'll say for Monday how we get the moment diagram. Basically, we can construct this from the shear diagram, and we'll talk about that Monday. All right, any questions about shear and moment diagrams at this point? All right, well, we're out of time for today and for the week, and I hope everybody enjoys their time off. Be safe. Respect the virus, and I suppose if you're doing fireworks on the 4th of July, don't blow your hand off. As always, though, I'll stick around. If anybody, you got questions about anything, you want to hang around after I start recording.
A question real quick.
Okay.
Are the moments zero where the shear starts and ends every time, or is it just for this case?
Well, we're going to talk about that Monday, but the moment is going to be zero. Basically, and again, we're going to talk about this Monday, but if you've got, when you look at the end of this beam, it's free.
Mm-hmm.
And at that free end, the moment's going to be zero. Typically, unless you have a fixed support, if you've got like a cantilever beam, where you got a fixed support here, the moment's not going to be zero there at that end.
Mm-hmm.
That's basically the only way. Or if you've got like a beam where you've got some concentrated moment, like 10 foot-pound moment acting there, the moment's not going to be zero. Wherever you've got one of those, or because basically you're going to have this reaction here, right? If this is A, you're going to have some reaction moment. Moment's not going to be zero. So basically, unless you've got a fixed support, or you've got like an applied moment here, those are only two times the moment's not going to be zero at the end. And yeah, we'll talk about that more Monday.
Okay.
But good question. Any other questions? All right, then I'm going to stop recording. And
thank you.
You too. Have a good break.
You too.